Welcome back to derivability. Let's take a look at sum and difference identities for the tangent function. Okay, we took a look at the same for sine and cosine not long ago on the channel, and those are exactly the ingredients we need to derive this tangent sum identity. Okay, and then we'll do the difference identity later. All right, so you guys recall that tangent is equal to sine over cosine, as long as the insides of the function are the same, the sum of those two angles, theta plus phi. Okay, as long as that occupies the insides of the tangent, the sine, and the cosine, then we have this good old identity, tangent equals sine over cosine. Okay, so what we're going to do here is we're just going to borrow what we have from previous work. Okay, so in the numerator, sine of theta plus phi, okay, that's going to be sine theta cosine phi plus cosine theta sine phi. And in the denominator, for the cosine of the sum, cosine theta cosine phi minus sine theta sine phi. Okay, now if you're not too picky, then this is it. This is our identity. Okay, except it kind of makes sense here to see if we can possibly write this tangent identity completely in terms of tangent functions. Okay, maybe we can and maybe we can't at this stage, but at least it's a reasonable thing to try and ask. All right, and I believe the answer is yes. I think we can do it. Okay. All right, now remember, to get tangents on the right side, we need to take sines over cosines. Okay. Now we can't do this for free exactly. Okay, so what I'm going to do is I'm going to multiply top and bottom by the same thing, which of course when I do that, okay, it's really equal to 1. And the same thing I am going to multiply by is 1 over cosine theta cosine phi. Okay. Now, a lot of times when you're working with trig identities, among other things, the first thing that you need to be convinced of is the step that we are doing legal? Okay, so hopefully you're easily convinced that the step that I'm proposing is legal, because after all, I am just multiplying by the number 1. Now, the second thing you have to figure out or understand is it's legal, but why? How is it helpful? Okay, this is where experience comes in. And here we want to have, inside of the main fraction written in the blue marker, we want to have sines over cosines. Okay, so multiplying by 1 over various cosine factors hopefully will move us in the right direction. Okay. Okay, so now let me use the distributive rule through the numerator and the denominator. Okay, so I have sine theta cosine phi, and then this distributive rule, 1 over cosine theta cosine phi. Okay, and then I have my other term in the numerator, cosine theta sine phi. And then again, this distributive rule, 1 over cosine theta cosine phi. So what I've done is I've distributed this in through the parentheses. Okay, and then an identical maneuver happens in the denominator. Okay, I'll just prepare what I need in the blue marker first. Okay, and then my distributive rule, as in the numerator. Okay. All right, so now we are getting some good action to happen here. Okay, so notice that each of the items written in the blue can be thought of as fractions whose denominator is equal to 1. Okay, that might make things just a half step easier for you to see what's going on. Now when we do that, I have a fraction times a fraction in the upper left here, and we get cosine phi to cancel. Okay, and then as we move through the various 4 terms here, okay, the next one in the numerator, I'm going to get a cosine theta to cancel. First one in the denominator, I actually get everything to cancel, and then nothing cancels in that second term in the denominator. Okay, but what we get to start happening here is my remaining terms here are a sine divided by a cosine, sine theta, and then down below cosine theta. Well, that is just exactly tangent theta. Okay, second term in the numerator, same thing happens, except it's sine phi divided by cosine phi. So that's tangent phi. Okay, first term of the denominator is just going to be a 1. Everything is canceled. And then the second term in the denominator, I'll actually have both tangent theta and tangent phi. That is the product. Okay, when I recognize the sine theta over cosine theta and sine phi over cosine phi. Okay, so maybe you were expecting this to be more work, but it turns out it's not. This is our tangent sum identity. Okay, all right. Now, what about the tangent difference identity? Well, if we kind of play this kind of slick, then we kind of get that as a bonus. It's really not that much extra work. Okay, what I want to imagine for a tangent difference identity is I'm going to change the sign of phi to be negative phi. Okay, so you can see how I did this on the left-hand side. Okay, and then I'm going to change the phi to be negative phi over in those 2 cases over there. Okay, well, tangent theta stays the same. Okay, the 1 down there stays the same, but because tangent is an odd function, okay, that means that any negative that you might imagine inserting, so tangent negative phi, that negative would come out front and multiply out front of the function. Okay, so my numerator is going to be tangent theta minus tangent phi. Okay, downstairs I'm going to have the 1, and then if I imagine my phi becoming a negative phi, well, that negative will come out front, multiply the negative in front of the product, tan theta, tan phi, so negative, negative makes a positive, and before you know it, now we have our tangent difference identity. Okay, so I'll just put a star on the first one and a smiley on the second one there. Okay, all right, so there you go. Hopefully this has been helpful. Okay, we got it done on one screen even. It didn't take too long. All right, so in the scheme of proving trig identities, kind of the standard trig identities, maybe the next thing you might be interested in would be double angle identities for sine, cosine, and tangent. So that's probably on my menu to make a video here soon. So if that's something that interests you, stay tuned. Bookmark the page. Better yet, subscribe, and hope to see you back here again real soon.